AP Physics 2, Unit 2, which is thermodynamics. Progress check, multiple choice set B. A lovely problem set, culminating in number 19. So 19 problems we got to look at. Let's go crazy and start with number 1, shall we? A PV diagram. Constant pressure. Work done by the gas, because the thing expands. So that would be energy out of the system. Through work. But since the pressure is the same, you could end up, so there could be heat put in so that the ending pressure would be less. So the work will be negative, but you could do enough Q to make this whole change increase in, it definitely would be an increase in internal energy. So, all right, there's a bunch of stuff I just noticed when I saw it. The graph shows the pressure as a function of volume for a sample of ideal gas is confined in a cylinder. A movable piston sits on top of the gas, and the piston can move vertically with negligible friction. The weight of the piston is significantly less than the force exerted by the gas on the piston during the process shown. So that's why you do that. Which of the following is true of the acceleration of the piston during the process? Let's see. Pressure doesn't change. Well, that's because you don't change the top. What's a significant... Acceleration is not decreasing. The acceleration is increasing. No. Yeah, I would buy that. So, it's got to be... First of all, there has to be an acceleration because the weight of the piston is significantly less than the force exerted by the gas. Okay, so the force up is going to be more. So there's going to be an acceleration. So that rules out this one. These two talk about there's a change in the acceleration. If there's a change in the acceleration, I wonder what this would look like. You'd still maintain, you still maintain this, but would it... I have to think about that. But the force, the net force has to stay the same. Pressure inside, pressure in... Is the force going to get less? It's an interesting question. I'm willing to go with this one. I could argue this one in the sense that as the volume increases, the pressure on the underside of the piston goes down, possibly. And if that's the case, the acceleration would decrease, but it would still increase. It's fine. I could talk myself into this one. We'll go with this, but I could talk myself into this one for sure. All right. Number 2. Okay. All right, so when it all reaches equilibrium, this block keeps the piston from moving. That means the total downward force by the block and the piston, their weight, equals the upward force by the gas. Well, they give me the pressure inside is this. So this force by the gas is simply going to be the pressure times the area of this piston here. So there's the area. So I have 3 times 10 to the 5th pascals times 0.005 cubic meters, square meters, I should say. With the 5 and the 3, the 1500 should not be a surprise. We'll just double check it. 3e5 times 0.005, 1,500. So just recognizing that that downward force by the piston has to be equal to the upward force of the gas if they're in equilibrium. Okay, so cylinder while it's in the ice water bath and placed in a hot water bath. Okay. The system slowly comes to thermal equilibrium with its surroundings. The forces exerted on the piston once the system reaches equilibrium are shown in the figure. What is the relationship among the forces exerted on the piston? Well, if it's reached equilibrium, then this and this together, the two downward forces, have to equal the upward one. Yeah. Really, hot water, if that piston's in equilibrium, I don't care where it is. Right? Because once they put it in the hot water bath, but it slowly comes to a thermal equilibrium with its surroundings. So, boom, there's no, that's not, part of that equilibrium is that it's going to adjust the piston if it has to, but once it does, it's in equilibrium. There's your answer, B. All right. Force of the gas upward has to equal the two downwards. All right. So A comes in, has a velocity like this when it hits. Then after the collision, it has a velocity same size but up. Well, let's do final minus initial. Let's see whether that makes sense. So my final is here. Minus my initial. So let's just draw this down here so it's not in the words. So my final is this. That's the vector that represents my final. They say A is moving towards the top of the page. Minus my initial would actually be this. Final minus initial. Now the question is, does that make any sense whatsoever? I was moving directly toward the top of the page. So here's my thought. Something had to take away all of its momentum in this direction and give it momentum in this one. So that's why they had to do this. What that force had to do is push to the left to slow this thing down, but also push up to move it up. And what I'm trying to figure out, but if you told me it was this, I would say that it was moving down. So it feels like it should be, well, let's see, which combination is that going to be? Let's see if one can really talk himself out of this one. So A, let's try this. Had this, right? Ended up with this. Some of them would be this. My only concern with this is that it seems to me that that force would have sped this thing up horizontally, and all it didn't change it horizontally, it got rid of all the velocity horizontally. And so I'm trying to think. These always do throw me for a loop a little bit. Let's see. So there's no doubt this makes sense. Something that is against the horizontal but is upward. So how could I describe? I think this is the right answer. That. Now the question is, let's see if we can find it. So that wouldn't be A. It would be, yeah, so here's the right answer. Okay, so C is the right answer. Let's see if Wellborn can do a halfway decent job of explaining why. First thought is this. This, for example, that force would move it up, would start accelerating upward, but it would do nothing to remove the horizontal. So it would be moving at an angle at that point, not straight up, because you have to get rid of that horizontal velocity. This one down here does that. It gets rid of all the horizontal velocity, but this is a stopped object. It wouldn't be moving up. We need something that does the two of these combined, really, which is why this one works. This component stops the horizontal velocity, and this component speeds it up. I was drawing a lot of vectors down here. And I guess just doing that, just saying, all right, I've got a complete, yeah, okay, so here's the final. Here's the opposite of the original. And then I should have done this and connected them like that. That's what it is. Okay. Numero 5. System consists of two containers containing different liquids. Blech. The system is insulated and no thermal energy is lost or gained from the environment. Okay. Liquid A has a density of that and an initial temperature of this, while liquid B has a density of this and an initial temperature of this. Which of the following statements accurately predicts what will happen once the containers are put into thermal contact? Well, so we got density. Go with an amount of Does they say the volumes involved here are the same? I don't see that. I see two containers, but they don't say they're identical containers. So the density is nice and all, but if you only have a teaspoon of it, it's not as much matter as, right? So, but the temperature, regardless, will be between 20 and 60. Let's see what we can find. After a long time, the liquids will have the same total internal energy. I don't think that wouldn't turn. You don't know the amount of material in each one, so I think that's why we have to rule that one out. It's tempting. After a long time, the liquids will have the same temperature. That we know. This would be, they'll have the same temperature, but we don't know the number of moles, so we can't say for sure whether they'll have the same internal energy. If you just separated them out or whatever. Thermal energy will be transferred from liquid B to A. It'll always go from the hotter to the colder, so it's going to go from A to C. Yeah. So this one's a definite throwaway. Always goes from hotter to temperature to lower. This is a dangerous part answer here, but this and this are going to definitely work. Figure shows the movement of a fluid through an automobile engine and a radiator. The system is designed to prevent overheating of the engine. Which of the following claims correctly describes the energy transfer process involved? All right. Thermal energy is transferred out of the hot fluid in the radiator, and the resulting cooler fluid is then used to cool the engine. Okay, so the hot fluid coming in here radiates its energy out to the environment, increases its surface area, makes it easier to do that. And by giving up that heat, it comes out cooler. Okay? Thermal energy from the air is added to the hot fluid to reduce the temperature of the hot fluid. Cold never gets added to hot. That's not a thing. Energy will flow from the hotter stuff to the colder. So no. Hot engine adds thermal energy to the cool fluid, which reduces the temperature of the engine. So yes, if the engine puts heat into the fluid, then that's some of the heat it had. So the engine itself becomes less, raises the temperature of the cool, hot, and the whole cycle. Okay, so yeah, that's why I like that one too. Not just because it has a nice box over it. The cool fluid transfers thermal energy to the... Well, no. That's saying that cool is somehow flowed... No. Nope. All right, number 7. Sample of an ideal gas is contained in a cylinder with a movable piston. The gas expands, doing work W on the piston and absorbing thermal energy Q from its surroundings. All right, got Newton's first law of thermodynamics here. Which of the following identifies and justifies the correct form of the first law of thermodynamics during this process? Okay. Well, let's just kind of look at it ourselves. So we got change in internal energy. Is Q in or out? Okay, so now we got to figure out the signs. So anything that has energy out needs to be negative. Anything that energy's in should be positive. So when gas does work by increasing its volume, it gives up energy to do that. The gas expands. So that means this is negative because it took some of its energy and gave it up to do that work on the piston, and absorbing thermal energy from its surroundings. That's going to be a plus Q. So, all right, fine. Because thermal energy is transferred to the gas and work is done by the gas. All right, so they don't say that they're equal. All right. No. So yeah, this has to be the correct one. 8. PV diagram. Graph shows pressure is a function of volume for a sample of an ideal gas cylinder. Which of the following correct about the net work done by the gas during the cycle shown? All right. This is an expansion, so this is work done by the gas. We'll call it vertical lines. The work done on the gas, which is energy back into the system, is under this line. We'll make them horizontal. Okay. So the net work done by the gas is right in here. Let's see what they say. Is equal to the area under process X. No, that's good. If they said just the work done, but they said the net work done, is equal to the area under Y. No, that's being done on the gas because it's being compressed. Is equal to the area enclosed by the cycle because the net work is the work done by the gas during process X minus the work done on the gas during process Y. Cha-ching. D. It is equal to the area defined by the axes and the corner of the cycle at the upper... What? What? Oh, no. I'm not even going to try to entertain that. Nine. Cylinder is fitted with a low friction movable piston and filled with air at room temperature and atmospheric pressure, as shown in the left figure. Okay. The initial volume of the cylinder is 0.2 cubic meters. The bottom of the cylinder is placed in an ice water bath, as shown in the right figure, causing the volume to decrease to 0.15. The atmospheric pressure is, all right, what is the work done on the air inside the cylinder during this process. All right, interesting. So before we look at the answers, let's see. Well, PV equals nRT. Pressure stayed the same, atmospheric. So that's constant. Temperature dropped, so the volume dropped. So I can get the change, and these two don't change. So the delta V that they give us here, basically, should be the change in temperature as well. But we should verify it. Well, you know what? Wait a second. Cause for the initial volume of the cylinder is this. So wait a second. From that, is there a way to get? I think I got it. See if this works. See if this works. We may not need this. Okay. Work done on the air and this. When do you just need the work done? Well, a force is applied over a distance here. All right. What would that force be? Well, that force would be, we could look at it as the equal to the atmospheric pressure. We'll do it this way. Pressure atmospheric times pressure times area. Area of this, I assume. Yeah, I'm assuming. Yeah. And then that would be that force. The distance would be, this is the trickier part. It would be the area times whatever distance I'm talking about. That'd be the, well, no, it would be this. It would be, no, ready? It would be the volume, ready? I take it back. The volume of this would be the area times whatever distance change. So the volume change is going to be whatever the area is times this. All right. But you know the volume change. It's 0.05. You don't know the area. But that 0.05, let's see, divided by the area is your distance that it dropped. So here we have the force by the atmosphere. Here we have the distance, which we're going to write as 0.5 over area. And we see now why they didn't need to give us the area, because we're going to divide out. So it's atmospheric pressure times the 0.5. 0.05, I take it back. 0.05, careful. Let me see what that is. My calculator fell. I can go get it. There. All right. So atmospheric pressure is 1 E5 times 0.05. That's 5,000. So I get a work of 5,000 joules. Now, if it's done on the gas, what is the work done on the air inside the gas? It would be negative, because if it's looking at it from the air had work done on it. I could see it being negative at least. So let's take a look and see what our options are. All right, so give us some positives and some negatives. Work done on the air. Yeah, because the work done by the air would be negative. If you were the air, your work done would be negative, but the work done on you would be positive because somebody pushed. All right, so I would go with the positive 5,000. Think of it this way. The force, the atmospheric pressure is the thing doing the pushing down this way, and the displacement is down this way. Same direction, should come out positive. That's another way to look at it. Tricky little question. Number 10. Process W, 1 cycle per second. 1 cycle per second. 2 cycles per second. 2 cycles per second. Okay. A sample of an ideal gas can take the 4/3. Okay. Which of the following correctly ranks the energy E transferred out of the gas? So that would be work done by the gas. Okay. So we need the net area here. Net area here, net area here, and the net area here. But in this case, do they want the answers per second? So we're assuming in a second. So this, whatever area we find is fine. The same with this. These two, whatever we find, we're going to double because they have 2 cycles of it every second. So this would be 3, right? This is V1, 2, 3, 4. Yep. So this would be 3 VOs, and this would be 3 POs. And that would be 9 PO-VO, but it's 2 cycles, so that's going to equal 18 PO-VOs. This looks like the same thing, so that's going to be 9 PO-VO. This is going to be the same thing except half of this one, so that's going to be 4.5 PO-VO. This gets the same thing but doubled, so that's 9 PO-VO. So I would rank them with Y would be the largest, followed by a tie between W and Z. And bringing up the rear would be X. That's what I would say. Let's see if I'm correct. They put energy in there, but they get the idea. Yep. All right. Moving right along to number 11. PV diagram. Student has a sample of gas in an insulated cylindrical container with a movable piston. Student compresses the gas by increasing the force exerted on the piston, and measures the pressure and the volume of the gas. The student needs to determine the work done on the gas. Which of the following describes the correct analysis of information from the graph that will determine the work? This is the work done on the gas. So E starts pushing it, and compresses it. So it goes like this. So the arrow direction here is this way. Because that's work done on the gas. It's compressing it. Which line describes it? So I would need, I'm thinking, the area under that curve. Let's see if they have an answer that describes that. Multiply the average of the pressure data by the average volume. No, I don't think that works. If you could possibly, yeah, so you can't even do it. It's like a triangle, no, because you get, I don't think so. I don't think that's going to work. Multiply the average of the pressure data by the total change in volume. Add this to the product of the initial pressure and the total change in volume. Multiply the average pressure data. So that would be in here. Times the total change in volume. So that would actually find you this area. But you'd still need this. Add this to the product of the initial pressure here and the total change of volume. This being the total change? It might work. Seems a little complicated though. Multiply the total change in pressure. So far I'm not, if I was doing this cold turkey and I didn't see the right answer here, this one, I could rule this one out. Not so sure yet on that one. Because it sounds like they're at least attempting to describe, find the area of this triangle and the area of this rectangle. Multiply the total change in pressure by the total change in volume. That would only work if you had, if it was the line, instead of being like this, was horizontally across. That would give you the full area. So no. Multiply the total change in pressure by the total change in volume. Divide the result by 2. Okay. Okay, so they find total, they found this area, the total change in each, right? So this is the change in volume, no, pressure, this is the change in volume. Multiply, get this area, and then they say, divide the result by 2. Okay, so that gets them down to this area. Add to this the product of the initial pressure and the total change in volume. Initial pressure was here, times the total change in volume, so that would be this. So that would work. Now, how is that different than B, though? Multiply the average pressure here by the total change in volume. That's going to give you this area here. And then they're going to try to add on again. And I think that's going to be too much, I think. Yeah. So this part here is going to give them this area. And then they go on and they say, add this. Well, that's not going to work. You're already too big, and now you're adding on this. So, yeah, that's why that doesn't work. All right, D is definitely the right answer. 12. Student sitting on the ground, a few meters away from a campfire on a stool, on a cool, windless night. Student feels noticeably warm on the side facing towards the fire. noticeably cool on the side facing away from the fire. Which of the following models describes the primary method by which the side of the student facing towards the fire is warmed? There was not a solid object connecting him to the fire. There was no red-hot poker between his legs, touching the fire thing. So conduction's out. Convection is going to take thermal energy up in this case. Charged particles? What? No. Electromagnetic radiation, infrared. There we go. It's radiated. It's infrared wave. Same stuff in the heat lamp at McDonald's. All right. Ideal gas confined in a container with a movable piston. The graph of pressure, function of volume, shows 4 different processes in which the gas is compressed. Compressed in every case. Okay. Which of the following correctly ranks the magnitude of the work done on the gas? Work done on the gas is going to be positive because it was energy in. Now, who's got the biggest area? What it comes down to. Here, we'll attempt to do it this way. What the heck I do with my colored pencils? That's all right. So 1, area for 1 is this. And that's going to be 1, 2, 3, 4, 5, 6, 7 blocks. It's got an area 7. All right. 2. 2's area looks like this. 1, 2, 3, 4, 5, 6.5. All right, because this is 3. Cut in half, it's 1.5. So 1, 2, 3, 4, 5, 6. So 7.5. 1, 2, 3, 4, 5, 6 plus another 1.5. Yep, that's 7.5. So 2, 7.5. 3. Anybody here really feeling that 3 is a possibility? Are you really? I'll see. One, 2, 3. So 3 is 3. We'll do 4. Yeah, what the heck? We'll do 4. We'll do 4 in this. One, 2, 3. What do you know? 4 plus 3. So I would answer them as follows. I think the work done in 2 would be the biggest, followed by the work done in 1, followed by a tie between the work done in 3 and the work in 4. Let's see if that's the right answer. Oh, hallelujah, it is. Look at that. That, and that. We're getting there. We're on 14, 15, 16. I think we're going up to 19. We're on 14. We're getting there. Okay. Gas is in a sealed cylinder fitted with a movable piston so that none of the gas escapes. The cylinder and the piston are made of an insulating material. The cylinder is fitted with a pressure and temperature sensors. A fancy cylinder. And the volume of the gas, of the combined gas, can be measured from markings on the side of the cylinder. That cylinder is the Mercedes-Benz of cylinders. The gas is initially in a state with pressure Pi, temperature Ti, volume I. Piston is slowly compressed, and data are recorded until the gas reaches a final state. Temperature Pf, temperature Tf, and a volume, Vf. Graph of the pressure as a function of volume is shown, with dotted lines indicating isotherms. Looks like an adiabat. Adiabat. That line, that dark line there, looks like an adiabat to me. Okay, so an adiabat means no Q in or out. See, if you're really insulated, change the thermal energy, Q, work done. Now, in an adiabat, this is not allowed. Why? Because it's really insulated in this case. That's their clue. So if you do work, it's going to show up as a change in internal energy, which is going to be a change in temperature. So, which of the following describes the energy transfer process that the insulation prevents? So basically, it prevents any thermal energy from getting to the environment. Collision of the gas molecules on the inner surface of the cylinder cause disturbances of the molecules of the insulating material that travel through the cylinder, transferring energy to air molecules that hit the outer surface. This is an example of how heat gets out, and this is what the insulation prevents. So when it gets out, the gas molecules hit the inner surface. Those molecules vibrate back and forth along the surface, and then make the air molecules on the other side vibrate, and thermal energy gets out. That insulation prevents or reduces the motion by the molecules inside the wall. One way to do that is to make a vacuum chamber in between, so there's nothing to hit. An awfully complicated thing just to say, if you really insulate something, what does it not do? All right. That was 14, and now we're on to 15. Which of the following claims identifies the change in internal energy of the gas between its initial and final states as described, and describes the corresponding changes in the energy due to the work in heating? I'm assuming this question still goes with this. Seems a little vague if it doesn't. So which of the following claims identifies the change in the internal energy of the gas? All right, well, let's go back to this. There is a increase in the internal energy. Went from 180 bat to one farther away. You went from here to a lower isotherm to a higher isotherm. So that's an increase in internal energy. You did it without exchanging heat with the environment. So all of that change in energy came from the work done. Something along those lines is what I would look for. Internal energy increases. Energy is added to gas via work, and none is lost by heating. That's about right. Check. $16. It's empty. It's a tragedy. $16. Which of the following claims correctly indicates the changes in the collisions between the gas molecules in the cylinder wall that contribute to the pressure of the gas as it goes from its initial to its final state? Pretty sure we're on that same one. So, what we're seeing here is a change in temperature. It's an increase in temperature, which is going to also contain an increase in pressure. So what's the changes in the collisions between the gas molecules and the cylinder wall? Okay. The volume decreases, so you will get more collisions per, but you'll also get, since the average kinetic energy goes up, because the temperature goes up, the collisions, the force of each collision will go up too. So the volume decreases, so the number of collisions per unit time increases. The average speed of the molecules increases, so the average impulse, or the force required. So both occur. With a smaller volume, the collisions occur more often because they don't have to travel as far between collisions. And if they've got a higher temperature, they've got a higher kinetic energy, they're moving faster, it's going to require more oomph to bounce them back the other way, more impulse, therefore more force. So there you go. It looks like that's that for that question. Now, 17. Sample of an ideal gas is in a sealed cylinder, movable piston, and is initially at state A. As shown in the graph, P is a function of V. The gas's temperature at state A is 300. The gas can be taken from state A to state D, 3 separate paths. For which path, if any, is the change in the internal energy of the gas the greatest? Ladies and gentlemen, ladies and gentlemen, we have run across this before. This is your chance. You start here with a certain internal energy. You're going to end here with a certain internal energy. What's the internal energy here? PAVA. What is it here? 3 PAVA. So your change in internal energy is 2 PAVA. Your final minus your initial. Do you notice in doing that, all you needed to know those 2 locations? It didn't matter how I got there. There might be varying amounts of work done and heat put in, blah, 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 blah. The change in internal energy is path independent. It doesn't matter. So, none. The change in the internal energy is the same for all the paths. Because it is path independent. You can get yourself all worked up in that one. Trying to figure out work. Nope. Started at a certain internal energy in every case and ended at a certain. Changes. 18. I think we're working on this. What is the temperature of the gas at state B? All right. So we know here, right here, that the temperature is 300 Kelvin. And that's equal to PAVA. So at this state, we could write PAVA equals NR 300. Okay, but N and R aren't going to change. Here, I double it. I go 2 PAVA equals NR 300. Well, not equals 300, I don't know the temperature. But if I've doubled this side, and I can't change NR, I have to double the temperature over here, so it's going to be 600. So I would go with that. All right, try 19. Looks like it uses the same diagram. In which process is energy transferred from the gas to the environment by heating only? All right. So if there's a change in internal energy, and you can only do it by exchanging heat, that means the work piece here is 0, which means constant volume. So we need to find a process where there's constant volume. All right, well, constant volume processes are here and here. So the question one is, which one of those is energy transferred from the gas to the environment? All right. Well, if you can't change the volume and your pressure drops, PV nRT, if this can't change, then the only way you're going to drop the pressure down is to reduce the temperature, which is to let thermal energy out. So cooling is really a better phrase, but I would say C to D. And I would be correct. All right.